happens to be, about that long is what our communications antennas are. These leads happen to be just the right length for the perfect radio interference antenna. And we got that alternating current going back and forth. Now, you get a little bit of, depending on frequency, your bleed over, but you'll get the click, click, click of the spark coming through. So that's a big reason, the main reason that we have the shielding. So the shielding does kind of two things, right? One is it tries to give the flux, if you will, a path that goes into the ground to make it back for the magnetic field. But the other one is we are sending a amperage, voltage amperage, out to the spark plug. That's going to have to come back to the magneto. It is a generator in here. So it might go through the engine grounding framing. Both the plate that the wires are mounted to and all the connections are there. So there's a piece of, in a perfect world, whatever spark goes through the middle of the wire might be partially coming back through the outside. So these are a form of a coax cable as well, but if you got way down into the engineering, we don't want to get too deep with that because it's not true coax in the sense that the amp draw on the inside is exactly the same as the amp draw on the outside. But so you got a little bit of both sides of that on those cables so that they don't make those click and popping on our radios. I brought up an updated lecture here with some little bit better images in case you didn't get to see it when he was talking. So a Bendix magneto, and I set up here a Bendix and a slick magneto. The magneto itself has different connections where they're connected. The Bendix one, notice, has the springs that are in the magneto. So we've got an electrical connection there. It's obviously not a Molex, it's not a screw. So how do we make sure the power gets through? We're going to have something to take up a potential gap. The Bendix ones have springs in here. And these are the ones he was talking about that if they go away, oh man, is it a hassle to get them back in. Especially, imagine this is mounted on your aircraft with all that mess and you pull it off and the thing goes poing. Trying to find the thing in the first place is hard, but trying to get them back down in there is very, very difficult. That was the picture he drew. Where slick, they just have the connection point and the spring is on the wiring harness. So here's a Bendix, here's the old version of Bendix, and obviously these ones are pretty rough. There are no insulators on most of these. Here's what the insulators look like. But I took a picture. Notice it's crimped, and that is why we're not going to work on these Bendix mags. At some point, there was a kit where you could buy those witches hats, as they called them, and crimp a new one on. But it's just not something that's done. Usually you're buying a new harness. With these crimped witches hats, and what Dean was talking is the little bit of fuzzy wire hanging out the end of that crimped on, they can grab that spring and pull it out. So why we're talking about it again today is we do have some aircrafts in our inventory that you may be changing mags on that have Bendix mags with those springs in there. So for one thing, if you're taking off the wiring harness, be very careful with it and be gentle. If it catches, say your prayers and kind of adjust a little, hopefully you don't pull a spring out. The other main thing would be if you're ever putting a wiring harness back on a Bendix, before you put it on, it'd be a good idea to get a flashlight and a mirror if you can't see directly and make sure all the springs are in so that you got a good connection there. If it's a small gap, you might kind of get a spark in there without a spring. It's not going to work. It's not going to work well. It's going to mess up the mag and or the engine's not going to run right. So that is the blown up version of that. Now Slick brand came up with a little bit different witch's hat. These ones are what some of you guys are dealing with. So this is a Slick brand wiring harness that has Slick wires, which means it's got the coiled wire, and this is It's not threaded, which we'll do later, but that's pushed into that slick harness. So even though this is a slick harness, you notice no springs on this side, so it's a slick harness going into a Bendix mag. So everybody seeing that? Following along, you go, okay, yep, I see what we're doing there. So here's a slick mag again, and a slick mag is going to have the springs on the wiring harness side, so it's reverse. So just a visual for you there. Here's kind of like almost perfect for our cigarette thing. Our insulator, we want them to be tight. We actually don't really want a gap there. If there's zero gap, it's almost impossible to get your springs on. If there's too much gap, then it's floppy and they don't work right. So if you show me one like this, I go, oh, that looks really good. If it starts to get excessive, where basically, if with a little bit of jiggling, that thing can fall down sideways or close to it, hey, it's excessive. Because as we go to put it in, those things, they got to go in, and if it's too long, it starts jamming, it doesn't push in all the way. All right. Was that somewhat helpful with the blown-up view? Good. Check. This is Lab 8, which hopefully you guys all know, which I'm going to flip over to your lab schedule real quick. Well, not real quick. I'm just going to flip over to it. Somebody do computer screen for Christmas. I'll call Nick. So there is our normal schedule, which we all said we adjusted right because we had the day off. So midterms one day later on a Thursday, finals going to be on the Friday. So coming up this week, today, which is Wednesday, is moved down is how magnetos work. Tomorrow, we're going to be dealing with the disassembly of a mag. So we're going to go through with one of the slick boxes and basically demo how to disassemble your slick mag. So that's what's coming for today and tomorrow. You already learned how magnetos work. We're just going a little bit deeper with some of the components. Tomorrow, like I said, we will be setting up for the event. So they're telling me right about 9 o'clock or so is when they'll invite us, I guess you'd say, to help get set up over across the way. And with all of us, it should go pretty quick. Shouldn't take too long. For your lab timing schedule, I just want to point out, this day is now this day. So really we're at finish up Lab 8 today. So if you're on pace with us, on time, we're pretty much just at, hey, finish your wiring harness up. So that should not be too much of a challenge. And then start Lab 1. Lab 1 is just a matching thing. And then tomorrow was just a finish Lab 1, which we won't have a lot of lab time, but that's just a matching. It shouldn't be too bad. So pacing-wise, we're still pretty good. We're not crazy behind. Even helping set up tomorrow shouldn't be too much of an issue. With Lab 8, it does say to test it with the box. So hopefully you're not just running out there and assembling the lead as fast as you possibly can and trying to get it checked off and moving on. Hopefully you're reading your lab as you go through and you get to question 7 or whatever it says, and it says test it with the ignition harness box. I don't know if anybody did that. Some of the ignition leads are now back in the other box, so make sure you're following the lab and not rushing through these. If you get testing in the ignition lead on your O's and P's, you'll want to say, yeah, I did that. I totally get how that box works. And you just want to be able to do it. All right, I get rid of that one. Pull up this one. Slideshow. Whoa, it's like reverse order, really fast. Okay. Check. All right, we are off inspecting some, I saw somebody with one of these thin little ones that looks like the fancy straws you guys use nowadays, you know, if you're into reusable straws. And somebody had this one, and they were pounding their wedges back in. These are not the ones for pounding your wedges in, because when you do that, I even did this once, you oval out the end of that thing. So if you notice, this one's got a little bit where it's bent in, it's oval. That's not good. This is not going to work very well to shove in under the shielded now. So or somebody's probably going to have to take some time and work that back out and get it round. These are not the ones you pound with. These are the ones you pound with. Much thicker, heavier duty. It's a different piece. So if you didn't see that when Dean was lecturing, make sure you realize this is not the one you're pounding the wedges in with. You're going to ruin this, probably cut your wires. The big, thick one is the one you pound your wires in. And then along those lines, some of you guys' leads I'm inspecting, I'm grabbing onto the little springs, and I don't want to break the spring, but I'm giving them a little twist the other way, and some of them are just falling off in my fingers, and I'm like, wow, that came out really easy. So Dean demoed this tool. If you have a little drill bit in the backside, while you're pushing the spring in, you'll probably poke the drill bit into the back of your hand. So I don't recommend leaving that little drill bit in. It happens enough that just don't do it. But when you put the little wedge guy into here, you can take the other end, you put it in the end, that holds it really nice, and now you've got a really good grip to push that into the silicone. These, as you're seeing, these are not threaded. So it's not like this is going to thread itself. Why it acts threaded is because the slick wire is spiraled, right? Spiraled the wrong way. So you don't have to thread this in per se, because there's no threads on here. It's pushing in, but if you work with the threads that are in the slick wire, it will go in easier if while you're working it in, you kind of give the wrong direction. It'll work its way down in there. So they're not designed to be threaded. They're designed to be a wedge so that it's thicker on this end than it is on that one. So I think what's happening on some of yours is you're getting them in, but instead of all the way in, so that the tiny little threads that you're going to put your spring on there, I don't think on the ones that pulled apart, I don't think those were bottomed out on the silicone around the wire. So a wedge, if a wedge isn't all the way in, it's not going to be all the way tight, and then I can pull it out. So make sure when you're putting these in that you get that pin all the way in so that the threads basically bottom out on the silicone. Otherwise, it's going to be easy for this to fall out when it shouldn't fall out. Everybody tracking with me on that?
I have a question on that.
Yeah.
Do you want it to bottom, like, do you want to compress the coil?
It's not so much compress the coil as,
Or are you talking about like the end of the little pin?
wrong brand. Let's see if I got a good one to show you. No, that one won't work. Might be this one. Nope, I didn't bring the right ones in here. If I draw it on the board, if there's the silicone part of the wire and you got the spiral on the inside, I think what's going on is on that wedge, some of you guys are leaving it so that there's wedge hanging out from the silicone yet. If there's the silicone and the wire, this little spiral part where your spring's going on should be touching right up on the silicone like that.
The coil sits out past the silicone three-quarters.
This coil?
Yeah.
No, you trim that off when you're done. That's an important part. The only reason you have this thing out here is so that you can guide your drill bits while you're drilling the silicone out. Once you're done drilling the silicone out, you cut that off, and then now that wedge should be the threads that the spring goes on, buried all the way tight. If you're not buried all the way tight, your threads are out here and your wedge is like that, we're not using that portion of the wedge, and the thing's not going to be tight. savvy, as they say. Okay. All right. All right, review a little bit. Who can tell me what this one is? Dual mag. That's right. And if this was labeled 1, and it makes it a little tricky, we'll say it's a right-hand turn mag. Which cylinder would this wire go to? 6, that's right. Which one would this go to? 3, and then 2, 5, 4. Okay, good. We're all tracking with that. You guys are doing great on the reviews. All right, it's review, but we're going to go a little deeper as well. So, is this a high tension or low tension system? Sure. So this one is high tension. High tension means we got the high voltage that's going to leave the magneto. Another way to phrase it would be you're looking at where the distributor is in relation to the high step-up transformer, so secondary winding. So our voltage comes out of the secondary through the distributor to the spark plug. If this was a low tension system, you would end up with that coil pack right out by the spark plug. So each one of those spark plugs would have its own transformer right out by it. So this is a high tension system. High tension essentially meaning high voltage leaving the distributor. We have our high tension system here. Is this drawn in full register or is it drawn in neutral? Neutral, yep. Full register would be the fullest flux going through our coil. So this is drawn in neutral, and now a spark happens almost instantaneously, but would you say this is sparking or not sparking right now? Sparking. How do you know, David?
Because the magnetic field has collapsed.
So what?
The magnetic field has collapsed because it's in neutral. So when it's in full register, the magnetic field is built up.
Okay, so his observation is being in neutral, just timing-wise, if you were coming over to here. So, yes, but we can be a little bit more accurate than that as well. Anybody else? What would the other clue as to, yup, it's sparking either right now or very close? I'm going to take the hand just because I saw it. There we go. Our contacts are open, or you could say just open, hopefully. So we're actually slightly after it sparked because it will spark right as those contacts are opening. So the giveaway on this one is, and it's kind of a funny drawing, but this cam's geared to the engine, and it has just opened our contact points. And we know we get spark when the points open. And the reason for that is the points are going to interrupt the circuit that's ground through the primary back to ground. So right at neutral would have been where we have our highest amperage through our primary circuit. So our amperage was just up at the highest amperage and we opened the contact points. So we went from the biggest flux field we're going to have to no amperage, contact points open, and wham! That flux field around the primary collapses, which is around the secondary as well because it's wired into the same piece of iron, giving us the highest voltage to do a spark with. So, yep, that is what we're doing there. I printed this into this one. I'm not sure if this is the right slideshow. I said the amperage to the secondary does not. Last week I had said the amperage through the secondary goes to the contacts or the condenser, and that was a misspeak. If we actually follow where our little electrons would go, we're going to jump the gap in the spark plug. Oh, you know what? Let's pick the cylinder that the distributor's pointed at. We'll go with this one. Oh, it's sparking. Here's your other clue. There's actually a spark drawn in on the picture. Fun stuff. Okay, so our spark has jumped from ground through our spark plug, through our distributor, cylinder 1. Our little amp guys would have been moving through here, and they can't go through here. They might be sucking a little bit off here, but they actually can go through the primary coil to ground. And you're like, well, that's a weird way to wire it, isn't it? And I go, yeah, basically what happened with the engineers is there are some of these systems that this side is hooked to ground for the secondary, and they work just fine. But the engineer guys, the little bean counters, or whatever you want to call them, maybe I shouldn't call them that, that's the accountants, they found out that, hey, if we wire the secondary in series with the primary out to ground, there's a little bit of EMF or back EMF as that field's collapsing in the primary, that it adds just a little bit more, adds a little bit of energy and spark to our secondary winding. So if you were going to follow the amp draw through your spark plug, it actually follows back through the primary coil to ground. So as we get a little bit deeper, we'll end up seeing these coils. And this one I just drew on there, how that thing is internally wired. So the loop that's on these coils is pretty much always grounded. Careful, because I could shock myself. On there, so on one side I got a loop, on the other side I got a square. So the loop is usually, I'm going to say always, just screwed to the shell of your magneto. You'll see when you take them apart. So that one's always grounded. It's connected to the primary. And then it comes over, the primary other side goes to the square one. And then the terminal, we should easily remember, that goes to the secondary because that's where we're pulling off to get our spark plug, spark from. That goes to the spark plug. So the question in your head whenever you grab one of these that somebody did a magic marker on like that is, shoot, which one was the secondary hooked up to again? I know it's hooked up to the primary, but I can't remember if the secondary is hooked up to the loop or if the secondary is hooked up to here. Maintenance manual might help, but there's a little trick for you. Notice this is square, and well, you know, it might be a bad trick. I better not explain it that way because on the newer ones they round it off. But you could attach this guy onto here if you wanted to. I mean, you might break stuff, but you could put those together basically. What I was going to say is you kind of get with its sharp edges. So could you cut yourself on this round one? Not really, right? So I'm not afraid of the round one. This is case logic with a Band-Aid on my thumb after I cut myself on a fillet knife this week. I can't cut myself on the round one. I'm not afraid of the round one. That's the primary. The square one has some sharp edges on it where I'm a little bit afraid I could cut myself. So kind of a silly way to remember it, but the secondary is always going to be connected to that square one that, just for me, sharp edges, I go, oh, okay, I could cut myself. Otherwise, if you're a visual person, just remember that drawing right there. There you go. So there's a couple different ways to kind of be thinking about how are they wired internally. Now remember, the primary is like 100 times less windings than the secondary. It's like 100 to 1. So you can try to take an ohm meter and read the resistance of the windings. The issue is one of them's like 100 times less resistance or more, and some of the ohm meters don't like reading through coils like that. It kind of messes with them with the induction and whatnot. So you can try checking it with an ohm meter. Sometimes it works. Sometimes it's hard to tell the difference between 100 and 100 plus 1, right? The meter might not read so well. That's just the blown up version of the same thing. So that's how they're wired.
Why do we have that condenser in there again?
tension system. And so just pointing out, our low tension system does get amperage, if you will, from our low tension coil, but after the distributor, you've got the step-up transformer to step it up to what is spark voltage. What's interesting on that one is the way they have it drawn. If you were going to try to follow the amperage or spark, you're going to come through the spark plug. You can go through the secondary. On this one, it shows it going right to ground. So most likely, our path is just going to go through here. But depending on how that's acting, you might get some back to ground there. But that's a drawing. If I was to ask you again, is this high or low tension? This is what you're kind of picturing in your mind for low tension. All right, one more. Well, let me double check here. Yeah, we'll do one more and then we'll take a little break. Prepware likes to ask what are the 3 circuits in a magneto. And they like to throw in their magnetic circuit. It's like, what? Magnetic circuit? Is that even electrical? Okay, sure. I'll entertain your thought. So magnetic circuit is our flux lines. So we would say, right now we're in neutral position. The way they have this one drawn is not the way a lot of your FAA ones. If I wanted to go from north to south, I'm going to have some flux lines here. I'd actually have some flux lines going through that shoe, right? But that's not a complete circuit as far as our magneto goes. They'd call that a short circuit. So it's when this turns and the neutral is north is lined up here and the south is lined up here. When the flux is going through the iron, through my coil, we're calling that the magnetic circuit. So one of the circuits is magnetic circuit. Then we have the primary circuit, and they're talking the primary wires. So that's ground through my primary, through my contact points, out to ground. We call that the primary circuit. And then the secondary circuit is essentially ground, spark plug, distributor. And we got to get back to ground. So in this instance, back through the primary ground. So make sure if you ever get a question that says, what are the 3 primary circuits? You're thinking, all right, right off the bat, magnetic circuit, flux, and then primary, secondary. Everybody with me on that? Okay, Austin, when do we get spark? Yeah, that's the generic one, and you'll have a hard time timing a mag to that. When is the exact time? Why does the magnetic field collapse? When the points open. We want to drill into everybody's head. We get spark when the points open. And the reason the magnetic flux field collapses is because the points opened. We don't have amperage in the primary anymore. So because we don't have amperage, that magnetic flux field collapses, and the collapsing causes the spark. This is, and we'll go back and forth between calling that contact breaker or points. The reason they call it points is if I was going to just highlight that right there, we'll study later on about inspecting the points, and when they say points, it's the little pieces of the contact breaker that are going to touch to let electricity through. You'll inspect those to see how smooth they are, or if they're corroded. And over time, we have got to where we said, hey, go inspect the points. Well, it's the point at which the contact breaker touches each other. That's why that word points gets in our vocabulary. So depending on what drawing you have, we'll see, what do they call it on this one? Here we are. Breaker points is the long way to say it. It's the contact breaker points, but we don't like to use a lot of words, so we get it shortened to points. Somebody might say breaker, so you pick which one you want to say, as long as we all know which one. Points, breaker, same thing. Is that kind of cleared up? Okay. Very good. All right, last one. We'll pick on Stephen. only because I didn't get the last part of your devos. I wanted to apologize, I had to sneak out early, but I appreciate you sharing yesterday. If the ignition switch, or you'd say the mag switch, is in the off position, why doesn't our magneto spark? A clue is this picture doesn't have it. That one might. Does that one have it? That one. Yeah, that one has it. The low tension one has it. So we go back to, here's our ignition switch. If our ignition switch is off, which is actually closed, we won't ever get a spark out of our magneto because when we look at it, ground up to the primary coil, that's the same thing that our breaker points are doing. So having the ignition switch in the off position is basically telling those breaker points, you're never opening. Now, I mean, physically they open, but in the electrical circuit of the primary, the breaker points are doing nothing now. They're going bang, 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 but because our ignition switch is closed, the amperage from our primary will just go through the primary, through our ignition switch to ground. Right? It'll do that. We're creating amperage in the primary of our coil, but it's not a fast enough collapse to give us a high enough voltage on the secondary to make any spark. So, all right, take a break. Come on back at, maybe about a 7-minute break. So come on back at 10 to 8. That would be 7:50. Oh, sorry. Collapse. Yeah. So let's imagine this is closed for a second. So this is spinning and it didn't quite open yet. And when I say open, close, we'll get deeper in here. But as this spins, it's lifting on these contacts to open and close them. So if you watch this one, closed, open, closed, open, closed. Okay? So while that's going around and that's closed, we've got a magnetic field and basically lines of flux coming through here, right? That's going to induce an amperage through here. So if we have amperage in a coil, we can use our right hand rule and say, let's see, I don't know, maybe the voltage is going this way, so I got a north, I got a south. I've got a flux field that gets generated around that coil. And if you notice, it's the same flux field on the secondary as it is the primary, right? So while I have amperage, I have established this flux field we draw that way. Now I open the contact points, I don't have amperage anymore because I opened the circuit, right?
So it means all the way coming to the ground.
Well, this is magnetic flux lines, right? So magnetic flux, because we have ground through our coil to ground. And this is where a normal electrical circuit, you'd say, where's your light bulb, right? In a magneto, we're just short circuiting this coil. It's not a high enough amperage that we're going to burn anything up. We're just forcing electrons from one ground back to ground. That's what we're doing. So it's a shorted circuit. And it's going back and forth, one way, the other way, one way, the other way, right? It's alternating. So when this is closed, we have an amperage. Well, an amperage through a coil produces this magnetic field. As soon as I open those points, I don't have electricity flow anymore, right?
Yes.
Well, no electricity flow, what's going to happen to that magnetic field? It's going to go away. We call it collapses. So that's the word we use when we say collapsing magnetic field. So any coil we have, if I put a voltage to it, while there's amperage going through, it'll build, and we draw that magnetic field like that. As soon as I cut a wire, this magnetic field that we draw is going to say, "Whoa, I'm going back down." And we use the word collapse because, well, when it's drawn, it's out. I don't know if we imagine that, if it's just a way to teach it, but that's how we teach it, is a very strong field will get further and further and further out. So if you have a very, very strong field and then we cut the wire, you can kind of in your head picture all those go voop, and then now there's nothing anymore.
Right. So that's when it collapses, then it goes to here and then.
So yeah, so when it collapses, I draw it just on this one. We'll do 4. This is set up on this primary, right? This is what caused it right here.
Okay.
But notice the lines still come out of it through that iron, because we still have iron here.
Okay.
And this is the secondary.
Okay.
So when that collapses back into the primary, all these lines of flux are basically collapsing across that secondary as well. So, and that's the step-up transformer part you have. That's what makes it from this to, maybe it was 200 volts on off to, oh man, this is 100 times more windings in there. So yeah, it's a weird, magnetos are strange in that we're actually stopping the power, and it's the collapsing field of the power we stopped that causes that secondary to say, I've got a lot of lines of flux that just went through me really, really fast. Well, lines of flux through a coil really, really fast causes a voltage. So it's back to that kind of Lenz's law of this coil doesn't really care if it's building or collapsing. If there's lines of flux going across the coil, it's going to create or it's going to induce a voltage. And because we collapse it very, very fast by opening the contact, it's a very, very high voltage. When this is closed, so for instance, when it's closed, when it's building, well, we still build lines of flux across it, and you'd say, don't we create a voltage then? And I'd say, yes, we do, but because compared to opening the contacts and very, very fast we don't have amperage, on the building side, it's more of a slow build as the magnet comes around. Now, I say slow, it's happening comparatively 100 times a second or whatever, but it's comparatively slow build. So if we were to go back to kind of the drawing, the magnetic flux lines are, kind of up, down. But when you take and open the contact, the amperage going through it is, these are coming up, and all of a sudden we open the switch and a change in amperage happens very, very fast. So that change in amperage is what we're using on the secondary.
So when you open it and it collapses, is that when it goes in here?
Exactly. Yep.
Or a question I had, why are they like this? Like if they're in the same.
Technically, that's drawn so you don't have visual problems. If you were to cut that thing open, what you're going to find is this primary wire runs like that. It comes out, and the secondary wire runs like this. You're going to be here 100 times longer.
But wouldn't you be building?
Okay, and then comes out.
Yeah.
So we visually gave you that drawing so you're not looking at this.
All right.
But inside of that thing,
So it doesn't matter if it's building
As
at
long,
the same time as building the primary?
no, the key is they're both wrapped around the same hunk of iron, if you will.
Okay.
So the magnetic flux lines or the flux field around both of them is actually essentially identical. I might go see if I can find one. We had some that you could cut apart.
Are there transformers where they have coil on this side and coil on that side? Like,
Yep, that's
kind of my,
these.
yeah, that's
that
kind
one.
of in my mind, like, why would, but I guess it doesn't really matter.
Yeah.
The whole point is you build it to collapse it. You
Yeah.
step it up.
The reason we do that on those is partially they're, I'm gonna use the word more efficient probably. It's a little cleaner. That's, where'd it go? We had one in here, didn't we? We're going back to here.
Secondary. So that
Remember the one where we could add wiring or take wiring off?
Okay.
That must have went back in the airframe box.
Yeah, that's okay. I wasn't sure if that messed with anything.
No.
If they were wound with the same core, but I guess not. I mean,
No. If anything,
still
the
just-
same core here. So, they actually have it inside. I'll pass that around because I can sit some.
So does that mean when you're building though, when it's closed, you have slight voltage at the distributor? Just not enough to spark?
That would be the idea. And I think it'd be fun to see if we can measure it. And it wouldn't be that hard. We could put a mag on the test bench. We would have to ground out the lead and just put a voltmeter across the spark plug and see what it says.
And the difference is when it sparks because
Extremely
quick.
high voltage, yeah, it cuts really quick, yep, exactly. Instead of a slow up and down. It's kinda like if I took a hammer to you and I was like,
jogging.
bang, 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 like that doesn't hurt. But if I hit you really fast,
High voltage.
maybe that's a bad example. Alright, I gotta grab a mag. I'm supposed to have one that the impulse coupler came off. Oh, here they are. I was like, I knew I had a whole box of them. All right, I gotta grab one thing off the bench and then we'll get rolling. I had a counter pin in one in here. I'm like, oh no. Okay, we're back. All set up. All right, I've got some stuff to pass around. Micah was asking, is it stacked like that? And the answer is no, it's not really stacked like that. We actually have one that's cut apart. I'm gonna send around. The primary winding you'll see is actually, I don't know what just happened there. If we were to turn this sideways, what you'll see is the primary winding was on the inside and the secondary is on the outside. Not that that necessarily even matters that much, but both these wires are essentially winding back and forth, back and forth, back and forth a zillion times. But you'll see it from the side on this one. And then I'll also send around the one that I drew on there just so you can kind of get a visual of that. Ooh, I got one on both sides. So one for you. And tell you what. Well, we'll send this back your way. Can we have a magic marker in our pocket? If you would, draw the coils on there. So the primary will go from this one down to this one. Secondary is over here. Okay. All right. Some of these old ones, ooh, visually, you can just see that thing's bad. Somebody dropped it, right? Some of the material they used to make them out of would crack. So just visually, you can say, man, that thing is bad. It's cracked. So if you ever get a crack in it, it's just plain bad. They went to kind of, I'm gonna say the newer version where they're plastic wrapped. And it's a little bit trickier to tell, are these good or are they bad? The Slick manual will tell you how to test them. It's back to most of the time you're not going to take them out anyway, and you'll learn a little bit why later on. But we talked about the cost of doing it correctly, right? But there is this little test box that we will deal with a little bit later in class that basically makes sure that the windings aren't shorted out to each other. So what we end up doing, see if I can get this on here right, and I'll show you. That'll go to negative. Positive. Don't want to shock myself. Alright. The way this thing is set up, oh yeah, I'm going to shock myself. In, out, to the primary. No, I got these backwards, I think. Hold that thought. I want to show it to you once to make sure you get how it works. And out. VO. Through the primary to ground. Secondary is ground. Alright, that should have worked. It might be I wasn't close on something. Busted. Well, I might have to come back to that in a minute. I'll come back to that a little later in the slideshow. But we can put them on a little bench like this that tests them. I'll figure out why that's not working in a minute. Maybe at the lab. Okay, the question Micah's been dying to have answered. What about the condenser? So, on our drawing, we have a capacitor that is in that is in parallel with our breaker points, right? So it's hooked up to ground on the same, the other side of the capacitor goes over and hooks up to the coil. So it's in parallel with our contact breaker points. You could say it's also in parallel with our ignition switch. And they look like this. On your lab when you get that far, and both on Moodle and I think the paper copy, it basically says don't take it out. It is threaded into the side of your magneto, and you're going to ruin the wires and everything else if you try to get this thing out of here most often. It's very hard to get it out. So you do not have to take the capacitor out here at SMAT, but it's threaded into the side of the magneto. Here's a picture of it threaded in. It's a pretty tight fit with that wire, so if you were to try to unthread this, where the wire connects to the end of the capacitor It doesn't like it and it often breaks. So do not take that out, please. What this is a capacitor. Normally we draw a capacitor and we draw the two plates like that in our old style of wiring diagram, right? This is a capacitor, but the way it would get drawn is that this wire actually is the same electrically as that thread coming out the end. So make sure that you don't think of it like that. That is not what's going on inside the capacitor. Absolutely not. That wire goes all the way through, and you've got one side of the capacitor and the other side of the capacitor, and it's just connected to the shell, which ultimately is threaded into the side of our magneto. So this is what's going on with the capacitor you have. Kind of weird, and it kind of warps your brain, right? But this is what's going on. So one side of the capacitor is actually the shell, the ground. The other side of the capacitor is the wire, which is both those 2 points at the same point. So that's how those are physically connected on the inside of it. So if you wanted to go test that capacitor, and they're pretty small capacitors, I think like 0.3 microfarad if I'm not mistaken. If you want to go test one of those capacitors, you're going to connect one lead to the ground, to the shell, and you'll connect your other lead from the tester either to here or to here. Your choice, doesn't really matter, right? So be aware of what's going on inside and how you have to connect that. The reason they do it this way is when we're on a diagram like this, one side of the capacitor is grounded, that's not a problem, that's the shell that's screwed in. The other side of the capacitor comes up to this side of our contact or breaker points. It's inside of our magneto, typically. And we say, well, where are we going to hook our ignition switch, our mag switch to this system? And what they decided was, if we're really creative and thoughtful, if we run the wire, through our capacitor, we can just put our P lead on the other side of here and connect it up. So, so that's what they do. So what they do is they're actually taking from the capacitor to the mag or ignition switch and going to ground. But when you physically connect them onto that thing, you're kind of like, am I hooking that to a capacitor? It's like, well, yes and no. The capacitor really has nothing to do with the ignition switch, how you're hooking it up. It's just how they conveniently gave you a terminal that happens to be connected to the coil side of the capacitor to hook your ignition lead up to. Everybody tracking me with that? Good. So don't think that you're hooking a capacitor up and running that out to your ignition switch. That is not what's happening. It's this out to the ignition switch. This side of the capacitor just goes to ground. Cool? Cool. All right, moving on. We call that the P lead that connects to the end of it. But think of it, I don't know why we call it the P lead. I might have to look it up. I should add that to the lecture next time. But the P lead is what's sticking out of the capacitor and goes to our ignition switch. If somebody wants to Google it while I'm lecturing, I'd be curious. Why do we call that thing the P lead? All right. Anybody want a gold star for the day? I either have to draw it or we get one of you guys to draw our complete magneto wiring system. You guys have seen it enough. At this point, you should be able to draw it. If you don't want to be the volunteer in front of class, in lab time when you get a chance, practice drawing these so that you go, yep, that, corner, yep, okay, I got what's going on. If you can't draw this from memory, work on it and get to where you can. So, any volunteers? Leo?
No, I was just saying P is for the primary winding.
Primary winding. Okay, thank you. So P lead, it's primary winding lead. We always have to shorten everything in aviation so nobody knows what it really is, I guess, right? Alright, David's thinking about it. He's like, I always like having you guys do it because then if we draw something wrong, you guys are like, wait, no. It's getting your brain to be engaged with what's going on. So I'll get you started and I'll give you a north and south magnet into, basically our coil is gonna be up in this section. So, there you go, you got started? Part of it's, remember, we're thinking through, we got 3 circuits, we got a magnetic, which I already gave him, so I gave him one of the 3 circuits. So are you starting with your primary or secondary circuit? I would,
This would be my secondary.
okay. Secondary. So that's gonna typically go through something to decide which spark plug, right?
Right. I'm not
So-
done yet.
Yeah? He's doing?
We'll go there. You want me to draw each individual spark plug?
Nope, you can just draw one.
Okay, cool.
Yep, a lot of the drawings, they just have one spark plug. And you can even just put SP or however you wanna do it. Just so we know what's going on. Ooh, we even get a spark out of
Yeah,
it.
why not?
Oh boy, we'll see if he gets the
No,
contact
no.
points right.
We'll skip that for now.
Oh, no spark yet. I mean, I liked it. Yeah, as a reminder, basically we have 3 components in parallel.
Right.
So this part should be super easy. You just got 3 components, you just gotta remember what they were. Oh, is that your capacitor? They're actually in parallel, so put
Yeah.
your capacitor right in line there.
Right.
Yep. There we
This
go.
would go out to my ignition switch.
Ignition switch, there we go.
Ground.
Out to ground.
And there you go.
Yeah, there we go.
Let me
You're,
think, and then nope,
yeah, it's, I mean, it's breaker points, however, maybe just label it breaker.
got that. So
You can either just label it points or whatever you wanna say.
better points.
Okay.
What's the abbreviation?
Cap,
Or I'll just
I
do
don't know.
condenser.
Condenser, that works. Cool.
Am I missing anything?
No, you're pretty much there.
Oh.
Okay.
Oh, hang on. There's something I am missing in.
Well, so our primary lead's gonna be connected to 2 things. One is always grounded. So if you wanted to finish your
Right,
primary,
so could I just do that?
yep. Yep, so one is always grounded, and the other one is going to all that stuff. So on your secondary, you have it connected to the secondary, which is cool.
Right.
So our secondary has to be connected to something.
Also connected to this coil, right?
Yeah, it's that point right
Oh,
there.
Oh,
Yep,
Wait.
so I'll change colors
Okay,
on you.
Okay, I got you.
And that's typically our square one, if we wanna call it that, right?
Right. Where would our terminal be at then? This would be our ground terminal.
So ground, so those 2 go into that. So if you're,
Okay.
so if you're holding the coil, that's a bad one. Ow, see? If you're holding the thing, the terminal off here is what's coming up to our distributor. The one that goes to both windings is typically our square stake on. That's going to both my secondary and my primary winding. and then my round one is just going to ground.
Okay.
So yeah, you got it. Anybody have any problems with the way you guys run? Cool. All right, you should be able to draw that from memory, just so you understand what's going on. The key is making sure that, hey, I just got three things in parallel. I got my points, I got my condenser, capacitor, whatever you want to call it, and my ignition switch. And the capacitor there is making sure that you don't draw it like you originally tried, where it's going through it, because it's actually connected where it's one side of the capacitor is the wire going all the way through to our PV. All right, let me erase that. Get to where you can draw that from memory. I don't know if anybody will ever ask you, but you'll totally understand the system better once you can. All right, so you pilots, a lot of the POHs after a flight, they have you do what we call a mag test. Who knows what a mag test is? All right, we'll go with Kuvar.
You just go to one mag and back to both.
What does it do when you go from both to one?
It just grounds one.
Grounds one out, so what does the engine do?
Drops RPM.
Drops RPM, yeah, it's not running as good. So the idea behind it is,
Making sure it's grounded.
yeah, you're grounding the mag. So we would say you're turning the mag off. We're eliminating those contact points opening. So we're saying, hey, I'm going to check. So part of it is we're checking if our mags work. When we go to just one mag, we have turned one off and we expect rougher running. So if we have rougher running, we go, oh, whatever one I just grounded must be working. And then we'll do the other one and go, oh, I also had rough running when I turned the other mag off. So like if I go from both to right, we're actually essentially testing if the left mag was working. Because when I go from both to right, I have shut off the left mag, and if I go from both to right, shutting off the left mag, if the engine runs the same, well, the left mag must not have been doing anything in the first place, correct? So it's not so much that you're testing if I set it on right, is my right one continuing to run the engine? What we're really specifically on a deep level looking for is we're looking for a slight drop in RPM, so that when we shut one off, we go, yup, it was in fact running, but the safety reason most POHs do it for organizations is that P-lead that runs from the engine all the way to your ignition switch, if that wire were to break, if a connection were to go bad, turning the mag to off won't shut the mag off anymore. It's not grounded. So what you're doing is you're confirming that not only were both mags functional, but also that the wiring circuit from your mags to your ignition switch functions. So when you go left, right, off, you should have the engine will want to die, and as a pilot you should be really quick and turn it back so the engine doesn't die and you're not stuck on the taxiway trying to restart the airplane with people lined up behind you. Don't ask me how I know, because if you got, it's a thing, and that's embarrassing. You're trying to do a hot start and they don't start when they're hot. So off just momentarily to make sure that, yup, the engine's going to want to die, and then we'll go back to on or both and catch it and make them both run. Okay. When does the spark happen? When the points open. So, when is that? It's right before top dead center on our engine, right? However many degrees before top dead center, unless we are starting. So we're going to talk about that a little bit. When we're starting the engine, the prop is not moving at 1800 or 900 RPM and just whipping around really fast. When we're starting, we're moving much slower. There is not a speed this has to run to start your engine, which is why we want to be very careful, especially in this class working on them. If there is fuel in the cylinder and I'm going forward, I can potentially get the engine to start just by turning the prop this fast. It does start better if you're going faster with a good fresh battery, but if the conditions are right, it will start. And the reason is the impulse coupler. So I've got a magneto here. Normally our engines only have one impulse coupler on one mag. It is typically the left mag. We normally start on the left mag, not the right mag. And what it does is this plugs into the motor just like any mag, right? But instead of it being a direct drive all the way through there, I think I have one here, we have a mechanism that does two things. It delays the spark, but also spins faster. So this one's taken apart a bit. You got the little shaft there. We'll go under the camera, then everybody can see it. Wrong one. All right, so you can see here with the key that as I turn it, things are going around. I'm turning backwards, so it's not so funny. But when I go forwards, I'll get to a spot. Now I'm going to turn my hand's still turning, but the shaft isn't going until it releases. Oh, that doesn't work at all. And then it goes really fast. So basically we get to a point where the engine is still turning slow, but the shaft is not until that impulse coupler releases. So what that does is two things. One is, well, it makes the magnet spin really fast, right? That click, that's the magnet catching back up with the spring. So we spin it really fast so that our lines of flux cut everything really fast. So that's one part of it. It spins it fast. The second part is it delays it, because normally my points would open pretty close to there. But once those pawls catch, I'm going past the normal spot the points would open until it catches back up. So it's those two things. It delays it, but then also speeds up the magnet. On this image, we got an impulse coupler, impulse coupler, impulse coupler, maybe impulse coupler. Not all of them do. Usually it's just the left mag. So here's a blown up view of our impulse coupler. You're going to take these apart and inspect them. This one has a cotter pin, so I can't take it out. This one does not. I'm going to show you how to take these off. When they're off, you want it to look like this, where the spring is neatly inside. You don't want it to look like this, where the spring is not neatly inside, or you'll have sore thumbs from trying to put it back in. These are an awful hassle to try to get that spring back in. There is an official way to do it with a piece of rod, and you're giving it is, I tell you what, it is a hassle. So I'm going to pass this around and you can play with it. You can try to put it back in there if you want to. You probably won't get it. Normally the spring is nice and tough inside. That is a heat-treated, hardened, if you will, maybe hardened's the wrong word, spring steel. So we don't want to take a pliers and grab onto that thing, because our pliers would leave a mark. It's going to leave a weak point. So we don't want to typically grab onto those springs with any sort of a pliers that could damage it, which is why it's such a hassle to put back in. With the pliers, it would be no problem. You just grab it and spin it in and set it in there, right? But that would damage it. So we want to make sure that spring doesn't come out. So we're going to take our nut and our washer off, and we're going to basically engage the pawls, which you'll see in a minute how they work. But in the forward direction, you're going to engage the pawls, and while that spring is tight, you're going to just slightly remove that until the teeth are clear. And when I say the teeth, it's these guys here, and when you have one in your hand, you'll see what I mean. So you're going to engage the spring, bring it slightly out, and then you're going to let the spring go backwards in a controlled manner. Once you do that, it pulls out and everything is in here nicely. Not such a problem. Put it back on, it's the same thing. The spring fits into a little slot in here, right there. So when you set it back in, your spring goes into that little slot. Make sure you get the right spot. Now I've got to go the direction I'm going to go. And there, I got it. Now realistically, I think it's normally twice, so that's one. And that's why it was so easy for me to do the first time. Two. Okay, I'm all set. I would reassemble this with the bolt and stuff. So that means when I go to take it apart, This is gonna be a little trickier because I'm tighter than last time, right? So I gotta get it slightly disengaged, not too far, Case, not too far. Okay. Okay. Oh, okay. Now I can pull it off. Okay? If I were to come too far out, the thing's gonna go boing, and then you gotta put it back in. And I'm gonna send you to Dean. And he's gonna say, no way, man, do it with Case. So, I'm gonna put this one back together so that you guys can, if you want, play with that during lab time. There. Woo! So that's how those come out. I've poinged about 4 springs, and it's a hassle. If you do it, you take this piece, you put it in a vise, and just basically work it around either with your thumbs or with a small wooden dowel if you don't want your thumbs to get really sore. And put it back in. If you're inspecting it, if you see damage around here or on the other end, you know you got a bad spring. Here's a little bit different view of what we got. Some of the images in your textbook they're just bad images. So what happens is what we call these flyweights or the pawls, they sit inside the housing of our magneto. When it spins really fast, the heavy part of them wants to swing to the outside. And when the heavy part swings to the outside, what sometimes they call dog legs, but they will grab onto that pin. I said that backwards. When the heavy part swings to the outside, it pulls the part that would normally hit the pin in. So once the motor's up to speed, the heavy part on this would go out, which means it's not going to engage the pin, and our what do we call this again? No, impulse coupling. Wow, our impulse coupling is not going to go ka-tunk, ka-tunk, tunk, tunk. So when you test your magnetos on the bench, we're going to have you test them very slow RPM, so that it's going ka-tunk, ka-chunk, 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 and you're going to make sure you're getting a good steady spark. And then we're going to have you run up the magneto so that the impulse coupler disengages. Basically, it's the weight of the heavy part swings out, and you're going to say on your lab, what speed did the impulse coupler disengage at? So that tachometer that you guys all measured voltage on, you're going to use that to say, hey, what speed did I switch from the impulse coupler going ka-chunk, 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 ka-chunk to, oh, it's not in use anymore. So that's what we're doing with these. Now, on the side of the mag, we normally are retarded, whatever the engine says, 22 degrees is common. If we have an impulse coupler, it'll say what the lag is going to be. So it'll tell us the difference from normal open to, where is it? Wrong way. It'll tell us the difference from normal open to, okay, how many degrees basically was that? And there's some engineering, it's not quite like you're just going to measure it. So 35. So let's say this is on my engine. And let's say it's on my Cessna 206, that's 22 degrees before top dead center. Now when is my spark going to happen when the impulse coupler goes? Am I going to be before top dead center, after, how many degrees before, how many degrees after? You math people. I got a before answer. You said what? 3 to 4 degrees before. Does anybody agree or disagree with that? 13 after. Any other takers? I'm going to go with Corbin on this one. So if I was 22 degrees before top dead center, but I put a 35 degree lag in there, I'm going to go from 22 before to, well, I'm going to eat 22 of those up on the 35, which is going to give me 13 left. So basically, instead of 22 before, is we're going to say, well, let's delay that by 35 degrees. So yeah, we're gonna be 13 degrees after top dead center now that the impulse coupler releases the contacts open. So on starting, we are not before top dead center anymore, we're after because of this impulse coupler. Everybody tracking me with that? Good. Delayed, it'll say right on there, 35 degrees. Let me double check something. All right, good. You got a break in it like a slide. That's a slick magneto. Slick magnetos use impulse couplers. Bendix magnetos typically don't have impulse couplers on them. They're just, hey, it is what it is. So a Bendix magneto is going to use typically, well, you know, it's going to be dependent on the model. So maybe I better not say typically. A 12 and 200 series that have two sets of contacts, they're going to have what we call, okay, here's the deal. There's a politically correct way to say it, and then that's how it's written in all your books. Ryan doesn't like how it's written in your books because his mother used to be a special needs teacher. So, in your books, they're all called retarded points. They're retard points. And it's like, you can't say that word. And I'm like, well, that's what the manual says. So, I only bring that out to say they're a little bit slower. So, they're a little bit slower. And you may or may not be able to call them retarded. They're just a little slower, okay? So, that's why we call them delayed points. They'll get it eventually. They're just a little bit slower. Now, the book is not PR, so it calls them retard points. They're retarded. So, anything in the book you see is they're retard points. They're called retarded. So what happens is, as you're spinning, your main contacts open, and then the little bit slower ones, the delayed ones, the retarded ones, they'll open just a little bit later. We're going to cover how those get wired in later on, but that's why if you have two sets of points in a Bendix, some slicks even went to two sets, you won't have an impulse coupler because the retarded points are going to be doing our job for delaying our spark. And we'll cover how far after we go, well, actually it's probably a different class, but we're going to take a little break. Come on back. Let's make it a 5-minute. There's not much lecture after this. That way we can jump back out into lab. We basically are covering a couple components before lab when you come back. Yeah. Q. Follow me. So, that's actually essentially your electrical connection. Yeah, so the way that sits, that's what touches on the coil, the secondary part of the coil. So it's actually a brush, essentially a brush that sits on the secondary part of the coil. So that makes more sense. Yep, yep, and we'll go over that, I believe, tomorrow. It does in the image, yeah. The trick with these is, and we'll go over it tomorrow. It's stuck in there pretty good. If I pull it hard enough, I'm just going to disconnect the spring and start getting the spring out. As I pull it and then get a hold of the spring, now I can spin it whatever way Chinese finger trap will release the spring, and it pops out. Once it's out, you can take that apart, and they might even have you measure how long the thing is. But yeah, so that's what they got going there. Get it back in, it's the same kind of trick. somebody, is that my drawing? Somebody drew it on. Connected one to both. Sparks. That battery?
On completion of FAA plans briefly summed and required, how many copies were normally prepared?
Maybe the battery went dead.
What is their distribution?
That could be.
This one, oh, I see.
So we're going through the booster.
Yes.
All we really care about is I gotta go through the primary coil out to ground. So, what did I do? Well, that was weird.
For what period of time must an aircraft run to maintain the records?
A little nervous for pushing that closer. It's a connection somewhere.
Where should a 100-hour inspection be reported?
That was weird. Where do you think the bad part was? Just tried to think, well, can't believe it's the coil because it worked. Don't get screwed with jumper wires. Okay.
Next question. About the drawing.
Okay.
Is this not too bad?
Yeah, so secondary, if you were to make it a little bit better, you would take your wire coming in to the center and then an arrow to each spark plug. Not that you need to, but
And when it would be,
yeah, whatever one's
Like
pointed at is
this
where
one.
the, yep, exactly.
then you would,
You'd have spark at, well, theoretically, you're pointing at that one for spark. Okay, so that way your distributor's finished drawing, right?
so but contacting this one,
Technically, it's not contacting, because it's like this, which we'll cover a little later. It's just the finger, and it just gets close to it. So those never touch, it's just which one is it pointing at. So there's ever so slight gap in between here that the spark still has to jump through.
but this would
The
be
spark plug's
spark,
out there, yep, exactly.
but that would be, I thought they spark when they're not.
So this is not grounding, this thing is just deciding which spark plug am I gonna send the spark to.
What documents must be
This is
prepared
not
for
actually
prior
grounding
inspection
out
for
per se, it's deciding which spark plug are we gonna send the high voltage to. So, ignition switch is open, so it'll spark when we get that far. Capacitors in there correct, so basically when this breaker point contact opens is when the spark happens. So that's the one that when we disconnect ground from the primary, so ground primary through the primary to ground, when I disconnect that ground for a complete primary circuit, that's where we get the spark, as far as timing goes.
Okay. And your ignition switch, when you open it, it would,
So our ignition switch, we close the switch if we do not want spark. Because basically what we're doing is we're telling that breaker point, however you want to phrase that, is there's always gonna be a ground through there. So we would still be theoretically building, collapsing, it's just it's not going fast like when we immediately open the switch.
Would that be according to depot and aircraft?
So this is out to the distributor basically, right?
This is the distributor actually.
This will be out to the distributor?
Correct.
Okay.
Yep.
So what's that, it seems like less resistance would be back to the primary to ground.
That's and that's where it goes, where is it actually going? The only place to go if it was going
Any
through here
circumstance
is actually in and out of the
more than
capacitor,
2 copies of a compact
which does happen.
required, and if so, when?
And that's why they say, what's the capacitor for? We used to say the capacitor protects the contact points from sparking. It also helps a little bit with some amperage. But yeah, realistically, the amperage through our spark plug is going through the secondary, through the primary to ground.
So the distributor, this is the ground, and then this is like our ignition switch, capacitor,
So,
breaker points.
yep, exactly. So that square one would be where these two wires here come together. Well, these two wires.
Well, then this would be the distributor, right?
So this square one
So, the answer
is
is,
Okay.
questions.
authorized to make it required
It's a kind of tough class because you guys are all fighting the Z monster. If you put this all in one class, it'd be crazy long, so there's a little bit of, you're introducing a little bit more each time you come through. All right. Got a bunch of really good questions during break, all of which we'll cover in the next 3 or 4 lectures. So I was just telling you guys, this class is a little tricky. We could just do a marathon 10-hour lecture. Right, yeah. So part of it is we're doing a little review and then we give you some more info, so that by the end, you'll know what all the components are in these. So for instance, on our impulse couplers, when I pass this around, actually this one there should be springs. I must have grabbed the wrong one. There should be springs that want to return these ever so gently. They're in there. They return it to the I'm sticking out, I'm going to be engaged position. If there's no springs in those, you probably have a bad part of the impulse coupler. So when you're doing your inspection, they'll ask about, are the springs working? And if you just take this thing and try to figure out how to make it go all the way around and try to keep going, part of it is you're going to bust the spring off. So don't go too crazy with those, but I'll pass that around. Did those two make it around the room? Yeah. Okay, perfect. Oh, that was coming the other direction. Perfect. All right, so we're going to cover some of the other components. This is a magneto tack drive. A little hard to tell from the picture, but the threads on there are basically the exact size to go in if you were to take out one of these plugs down by the magnet on our magneto. So you take out one of the vent cap plugs. So that means that the magnet is going to go whipping by this little deal here when it's running. Well, we can take that electrically and say, okay, I know my magnet is geared at, and we'd have to know what ratio in the engine, right? But somebody's going to do all the math and decide if that magnet goes by 2,000 times per minute, that means my engine's running at, and what mathematically ends up happening is probably about 2,000 times per minute because the magnet's got, anyway, it's all going to depend on, do you have a 4-pole magnet or a 2-pole magnet? What's the gear ratio to your mag? So that's a component that they put on the magneto to get an accurate tachometer reading on newer aircraft, so we do it digitally instead of with a cable running to the cockpit.
So, yeah, newer aircraft, would there be STCs for installations?
So this is a component that would come with an STC that you could add this. So say your old aircraft, you could add a digital tachometer, and basically you're going to buy this component, you're going to buy a little digital tachometer, and it'll come with a piece of paper called an STC that says how you install it and that it's legal.
So like Tier 6 to G1000.
Very likely the G1000 is going to have a component just like this on it. So it's going to read the RPM off the tachometer. Yep, exactly. Because we don't have a cable going into the back of the G1000, right? So there's multiple ways to do it, but this is exactly the kind of, and very likely the specific component that a digital flight display is going to use to get a tachometer reading. Yep. Make sense? Pretty cool. Back to these magnetos we're working on. These are like, this is 100-year-old or more technology. Like we can do better. We can, but they're very, very reliable and they work. So they're still on airplanes. As we get towards the end of class, we'll talk some more about e-mags, which are fun and cool, but they have a failure rate, right? All right, testing capacitors. We've done this multiple times before. Remember, the shell is 1/2 the capacitor, and the wire, you can pick whichever one you want because it's connected all the way through there. In that function, that's one wire, is the other half. So if you have a digital multimeter that'll test the capacitor, by all means, go ahead and test your capacitor with your digital multimeter. Some of them will ask for a breakdown voltage of what the capacitor is. And remember, when we test on that box, we can test the breakdown voltage. I thought I had a couple. Of what it is, but when we test on the box, the breakdown voltage, if we exceed the rating of the capacitor, say it should have a 300 volt breakdown voltage, and we go 100, 200, 300, 400, hey, this thing still tests good. 450, oh, now it's bad. Well, now it's bad, because we theoretically bled voltage through our capacitor, which might have left the carbon trail behind, and we might have ruined the capacitor. Might have. So, if you are going to test the breakdown voltage on a capacitor, you would want to know what's it supposed to be good to, and you don't go past that. You just go, yep, it's still good, and then you go back. You don't see what the breakdown voltage actually is, you just say it tests up to that level. So I'll pass these two around so you can just get a hands view. So a reminder on how this thing works. Just a quick reminder is you're going to go back down here to, let's see, this one is set up to paper mica test. So we're testing the breakdown voltage, and you're going to just turn the voltage up to whatever it asks for. If it says, hey, this one should be good to 250, as I turn up, if you remember the eye, it goes closed, and then when you stop turning, it goes back open. I believe is the direction it goes, closed, back open. And if it ever doesn't do the back to where you started, that open position, we're bleeding power through our capacitor, and the capacitor's bad. So go ahead and test the capacitor. Some of these random capacitors that are laying around here, if you want to go past the breakdown voltage, you theoretically could, because they're not functioning airworthy capacitors. If you want to test the capacitance of the capacitor, this one's got to come down to whatever range you're going to anticipate. And generally speaking, we're going to anticipate about 0.3 microfarads. So you'd end up on this setting, and then you'll want to make sure you're on that scale. So where that dial is pretty close, I think, to where you're typically going to be getting your capacitor reading. But if you have questions on that, grab me or Dean during the lab. We've done it in all the other classes, so this one's just a little bit of a review. Now, caution, safety-wise, as always, when you're finishing testing your capacitor, turn it down, and after you turn it down, they like you to short the two terminals on it, just in case something didn't work right. You don't want to charge up a capacitor to 400 volts and go, oh, the breakdown voltage tests fine, and then just disconnect it from the wires and stab yourself with it. No, like catch with someone. Yeah, that's what we don't want to do. At my safety briefing, they were talking about how we should be talking risk and safety all through stuff. Yep, that's right. You guys didn't see that. All right. I had this thing wired up and it was working, and then it stopped working again. So I got to go find. I think we have bad leads is what's going on. Just for the fun of it, we'll see if it goes again. Nah. So we'll get one that works with correct leads. I think we got bad leads, but here's the slick tester. Basically what we're doing, it's hard to see because the wire leaves, but I'm simulating in the slideshow this voltmeter lead being ground from a battery. So I basically gave you this picture if you want to review, hey, how do I hook that up? So we're going to put our battery power to in on the buzz box, and then coming out of the buzz box, we're going to go through our primary coil, so that's the round loop, so through our primary, and then that's just going to go back to ground. So whether we hook it up to the battery or a jumper wire, and then the secondary is basically hooked up to the same ground. This one is wired that way. So the secondary is going to go from ground through the secondary back to basically ground. It's just a complete circuit, just like your magneto is. So if you notice on here, ground through the secondary, and the terminal would come out just going to ground. So there's a couple different ways you can hook it up and make it work, which is why it can get confusing when you're staring at it. The main thing is we want voltage to go from the battery through the vibrating contacts through the primary. And then the secondary is just essentially ground through the secondary back to ground. We'll get it working and get you all showing it later. That's just a cleaned up picture. Okay, I was supposed to open lab 1 and 2. You can start on those. Like I said, we're going to do a lot more breakdown of these, so if you get a question you don't know, you can come ask me. There's one of them that Corbin already did. There's a drawing in there that looks like a screw or a bolt, and he's like, it says brush, and the reason is, here's our distributor block. Our distributor block is going to sit in our magneto so that that little carbon brush rides on, I guess it's this way, rides on the terminal. So the power coming off of our secondary feeds into that carbon brush, and that carbon brush is what's connected to the finger that ends up pointing to a spark plug, right? So in the picture it looks like it's a screw, but this carbon brush is actually, which way do I gotta go? That way. It's connected to a spring. So you got a brush and a spring, and they'll have you measure the length of that brush when you're doing a 500 hour or whatever it is. What's tricky is getting them back in or out. You gotta look really close at the direction that spring is, because if I wind it the direction that'll wanna collapse it, I'll actually be able to get it to go back inside this little stainless steel piece. Ooh, with a little bit of practice and a little bit of skill. Once you get it started, you can pretty much just push it in, and you push it in the rest of the way. On the way out, if all I did was grab the brush and pull, it's gonna disconnect from the spring, and now I gotta figure out if I got a needle nose small enough to get it. So on the way out, you're gonna pull it out far enough that I'm actually holding onto the spring now, and once I'm holding onto the spring, I could just pull it out, but I'm gonna stretch the spring, so I'm gonna look really close and say, which way do I gotta spin it to collapse the spring? Oh, that would be that way. And if I collapse the spring while I'm pulling it out, it pulls out real nice. So that's one of the pictures if you're doing it, is there's that carbon brush and the spring. Usually I save that little demo for when we're disconnecting our mags, but it is a point that's some confusion. So if you want to see that, come see me. Otherwise you'll do it when you're disconnecting.